Hello everyone, this is Sarbajit Dutta and welcome to Educathea. So in our last lecture, we have seen how Thomas Young proved it for sure to the scientific community that light has to be a wave through his famous Young's double slit experiment. But then later on, certain events forced the scientists to rethink about their proposition. Experiments showed that maybe light can also be composed of particles, which was ironically what Newton had said in the very first place. One such experiment had to do something with why do things glow when you heat them up. Let's try to understand it with the help of thought bubble. So let's clear up the basics a bit. We can see an object if that object emits light directly, which reaches our eyes, or light from somewhere comes into your eyes after getting reflected from that object. Something radiates light when its temperature is higher than its surroundings. I mean, a candle is lit because its temperature is higher than its surroundings. The sun is bright because its surface temperature is higher than the surrounding space. These radiations are waves for the time being because Thomas Young proved them to be. Now all these waves have wavelengths. So does these radiations. Each of these wavelengths can be associated with a color like blue, red, green. Some of them can be seen by our naked eyes like the visible light, and some of them are invisible like infrared and ultraviolet light. The sun, for instance, radiates most of its sunlight in the visible part of the spectrum, and that's why our eyes have evolved to pick that light up. Maybe that's why visible light is visible. It also radiates invisible light which we cannot see. Secondly, let's talk about the objects on which light falls. When light falls on something, it is either reflected, absorbed, or transmitted. Let's keep transmission for the time being aside. It is to note that the color of light which reflects into our eyes is what makes objects colored. If nothing comes into our eyes, then we see that object as black. So black is not actually a color. It is the absence of any colored light coming into our eyes. For instance, now you see the screen to be red because red light is coming into your eyes from the screen. Now you see it blue because blue light is coming into your eyes. You see it black now because no light comes into your eyes. That's precisely the reason when you shut down your computer or mobile screen, it appears blackish because no colored light is emitted by the screen. Now objects that we see around can appear black also if it does not reflect any light coming into your eyes, which means if it can absorb all the light which is falling upon it. These type of bodies are called black bodies. Black because it absorbs all the light and appears black in color because nothing comes into your eyes. A perfect black body absorbs 100% of all the incident radiations. However, that's only one side of the coin. Let's switch sides now. Understand, if something absorbs light, its temperature rises. This is because even light is a form of energy which can increase the atomic vibrations in an object, making it hotter. The crucial point to understand here is that if its temperature rises above the surroundings, then it should emit radiations, as I have already discussed. And it does. Remember the phrases red hot and white hot we used to describe this effect? The hotter, the more glowing it is. This is actually quite ironical because I have told you that black bodies absorb all the light which falls upon it. So even it should get hotter and start glowing. In principle, a perfect black body will glow with all the wavelengths of light because it absorbs all the wavelengths. Now, wait a second. A black body is a bright body? Well, even I agree that the physicists have done a terrible job in naming this thing a black body. The crux of the matter is that it is only black when you are at room temperature because then it will absorb all the light and appear black. But when the temperature is high enough, it will start to glow and then it's no longer black. An interesting fact is that our sun is a great example of a nearly perfect black body. Strange, right? One of the closest black bodies that we have is actually the brightest thing in the solar system. This kind of radiation is called Blackbody radiation. Technically everything, even if it is not a black body, radiates some light when it is hot. Our body radiates light too. The wavelength which human body radiates at room temperature falls in the infrared region, and that's why we can't see people in the dark. But you can with the help of infrared goggles. You must have seen them in movies. A fun fact: snakes can sense infrared light, which helps them to detect their prey. Do you know why? Well, that's the job of biophysicists, and I'll leave it to them. So now we have a fair idea about what a black body is. So a black body is an idealized physical body. Idealized because nothing in this universe is a perfect black body. You must be wondering then, why do we care about such ideal stuff in nature? If an ideal black body does not exist in nature, then why to care about it? The answer is, calculations are very simple when you take the ideal case. And the real cases are not very different from the ideal cases. So if you know what happens in the ideal situation, you can make a guess of what will happen if the situation is real. And that's why we care about ideal stuff in physics. So black body absorbs all the radiations which fall on it, and it emits all the radiations when you heat it. Now one must note that it is not always important to have a black body which is black in color. Yes, if you paint something with lamp black or platinum black, then it absorbs around 97 to 98% of all the heat radiations. But then you can have a clever method of making a black body like this. This is called a Ferri's black body. This is a very interesting mechanism of making a nearly perfect black body. It absorbs around 99% of all the heat radiations. Let's try to understand how this works using our favorite thought bubble. Ferri's black body is a hollow, double-walled metallic body coated inside with lamp black and polished with nickel on outside. Radiations entering through the small hole are completely absorbed due to multiple reflections. When heated, the hole gives out black body radiations too, as expected. Now let's visualize these black body radiations graphically. We plot energy per unit area, per unit time, per unit solid angle in the range lambda to lambda plus d lambda versus wavelength. The energy strangely only depends on temperature. It does not care what material you're using. It does not care about the shape, size, and extent of the body. It pays no heed to what pressure you're imposing and other physical conditions. It emits continuous energy over a range of wavelengths. Let's note down the observations that we might make from this graph. Number 1, at each temperature, a black body emits continuous heat radiation spectrum. The energy is not distributed equally among all wavelengths. Number 2, the energy associated with the radiation of a particular wavelength increases with increase in temperature. Number 3, as wavelength increases, the energy emitted increases, reaches a maximum for a particular wavelength lambda m, and then decreases. Number 4, the wavelength of maximum emission lambda m shifts towards the lower wavelength side as the temperature of the black body increases. Lambda m into T is equal to a constant. This is called Wien's displacement law. Area under the curve represents the total energy E emitted by a perfect black body per second, per unit area, per unit solid angle over the complete wavelength range at that temperature. This area is found to increase with the fourth power of absolute temperature. E is equal to sigma into T to the power 4. This is known as Stephen's-Boltzmann's law of heat radiation. So that's all about black body radiations.
Thank you so much for watching this video. Do not forget to like, comment, and share this video with your friends as much as possible. And also don't forget to subscribe to the channel, because that would serve as a motivation for me to come up with more such beautiful videos. Also kindly press the bell icon over there so that you get a notification each time I upload a new video. Don't forget to check the description box down there for more updates, and have fun and enjoy science.